nice green beans that I thought were green beans, and I chewed a few of them and realised they were chilies. A few ice creams seemed to help. So anyway, we'll keep moving. I hope flames are not coming out of my mouth. So we've had a pretty good couple of days and gone through failure modes and different types of instrumentation and different ways of doing visual surveillance. And now we're sort of getting to the pointy end where we want to actually use the data. So we've got a session here, data analysis and use. And the panel is going to be chaired by Sparsha Nagula. Sparsha is a project research engineer with NGI in Oslo, and she has pretty good qualifications with a summa cum laude PhD from Germany and the Telford Gold Medal. She specialises in computational geomechanics, focusing on numerical physical modelling. Dr. Nagula has expanded her research applying predictive probability-based random field framework to assess the safety of tailings dams. So she's in a very good position to chair this meeting, this next session, which is going to be a panel with, so we want to call up Edgar. Don't go, Edgar, you're on the panel.
Yeah, I'm just going to practice the panelist because my right layout, but I'm not here.
Yeah. Oh, okay, yeah. We need Leandro, Malcolm, Vinod. You're up too?
Yes.
Oh, okay. Come and sit up here. And Manuel. So, as soon as they come, we can start the session.
How much time do we have, David?
40 minutes.
Okay.
Yes. Maybe actually, you want to try
I'm the panelist.
maybe 35 minutes.
We are waiting for Manuel.
I think you can start.
Yeah, start.
Yeah, it's okay.
Okay, we cannot fetch
It
him.
might be quicker without him.
So very warm welcome to everybody. We can see that we have a celebrity status panel here who kind of decided to come a bit late and the participants are early. So hopefully the session is going to be worth it. I kind of got this feeling that we have mostly kind of discussed quite a bit of data interpretation and use, but there are a few pockets which might be interesting to discuss. The slides were already prepared, so I quickly try to run through them so that we kind of set the mood, and then we kind of hit on to with the panelists. There you go. So this could be what could be interesting to kind of discuss. Why, what, and how are we supposed to monitor? What is enough data? This was kind of pulled up quite a few times. Like how good is data? How do you know it's good? And then how do you really use this data and interpret in a way that it can help you kind of develop trigger action response plans? And can you really monitor or have a precursor which tells you that there is going to be a sudden or a brutal failure, which is very, very critical for tailings dams. So we try to look into this, but before that, whenever we talk about data in general, there is a cycle which we have been discussing over the past few days. So the first thing is we need to design instrumentation. So we need to design what are we trying to figure out from the instrumentation. It's just not because the instrument exists, you start plugging them just because we can. The first thing is if an instrument doesn't give you an output which is relevant, it's basically not needed. So that's where you start your design. And then you basically pick which instruments can give you this kind of an output. And then you design where they should be strategically kind of located. The next part comes in with installation. So the installation has to be carefully done in a proper way so that the instrument kind of performs the way it should. So we spoke about, like, Pierre kind of gave us an insight about how instrumentation installation can go wrong. And we saw that it can go wrong in a million ways. And there are even more million ways to kind of worsen it even further. And then the main point is instruments don't live forever. So they basically, okay, Anshad, you're supposed to be on the panel. Sorry. I saw you in the audience. I'm like, what is he doing there? And then they don't last forever. So we need to keep a track of how last they are going along, and also keep doing a health check that they are behaving the way they should be behaving over a period of time. And the last bit is obviously you are pooling in so much of data. So everybody is happy to kind of get these fancy data from sophisticated instrumentation, but we need to have good infrastructure to basically hold this data and then start using it to interpret, which could be interesting for us in terms of issuing a warning or a precursor to something that might be kind of going wrong. And at the end of the day, we basically want to use it to develop a trigger action response plan. So that's where the interpretation part comes. And it was rightly highlighted in the last session that probably AI and ML is not there yet. Fortunately, we are not losing our jobs. So most of the people who work with the designing or the interpretation are still going to keep their jobs until maybe the coming 1 or 2 decades. So with that, it's maybe interesting to kind of open the panel to see, maybe this has already been discussed to a part, like maybe not how much of data is good enough data, but what kind of instrumentation and how we should be careful on installing this instrumentation. So maybe we quick kind of jump to the next section, which has not been covered, which would be like, what kind of phenomena are we trying to kind of monitor, and how good are ground sensors or remote sensing? What is like good from a ground sensing point of view, and what is good from a remote sensing point of view? And can we really predict brittle failures or anything that goes like, bam? Does having monitoring system or sensors on the ground or up in the air good enough to be able to at least sense that something is kind of going wrong? And if this is so, when do we actually, or the interpreters have the liberty to pull the plug and say, we stop operations, we evacuate, we have to take action? So that's part of the trigger action response plan. So how does this flow happen? And I think probably Malcolm can open, because he probably spoke quite a bit with how the failure modes need to be identified and how do we move to TARPs. Where do you think instrumentation definitely fits in somewhere? But where do you think the interpretation part, which is the most critical aspect of it, kinds of comes into picture?
Sure. Yeah, so I guess when you're looking at failure modes, as we've been doing, you're looking at, do I need piezometers? Do I need increments? What do I need in terms of the actual data? I was going to make a comment in the last one. Most clients, they love these plots of piezometer versus date, right? It's nice plots to up and down there. Wonderful. I say to every client that I have, I say, I don't want to see that only. I want to see what's driving the piezometer level, which is the water level, right? So I want to see a water level versus piezometer trend plot, so I can understand what's going on, so that I can then get a trigger action. I can say, hey, when it gets to that point there, you're in trouble. Or these are the limits of the response to data. And you're going to get historical. You're going to get hysteresis, right? Definitely. When it goes up, when it goes down. Maybe not for the decant ponds and stuff like that and tailings where they just keep going up. But on a dam, when the water is going up and down, you do get that hysteresis effect. So you need to understand what is your data showing you in terms of where is that point of this is too high, and what are we going to do about it? That's piezometers. I mean, inclinometers, you're watching it move. Can you ever actually pick up a brittle failure? I seriously struggle with that one. Maybe some of the instruments we saw now, the ones with 2 meters, maybe they're, if you're watching a pure pore pressure change, or you're watching something happening with the angles, or something there with the differential movement there, maybe you can pick it up and say something's happening there that shouldn't be happening. INSAR was supposed to be able to pick up KDF failure, right? Hindsight's a wonderful thing, always. But the more instrumentation you put on there, everybody thinks that's better and better. Actually, I don't think it always is. Because sometimes you get information overload and think, oh, this is too much. And you know what? You stop looking at the data. Unless you've got Canary, or you've got one of those systems that actually throws it at you and says, bing, here's an alarm, and get on with it, and figure it out. But the alarms are obviously set by what limit am I going to put on, whether it's a piezometer, whether it's movement, whether it's actual ground movement. I'm doing my survey and I'm checking this thing moving slowly, whatever it might be. Always you're going to have to try and, as an engineer, we're always told, what are your design limits? How much are you expecting this thing to move? And a lot of the time we don't know. Some of the dams I've seen recently that have 6 meters of settlement that they didn't expect. And you think, wow, that's a trigger action you're having. And it had to do a whole lot of emergency repairs for a dam. So sometimes things happen you don't expect. I talked about the dam that I had with a hole in the wall. I didn't expect that. But we fixed it, right? But we had an alarm, and I was the alarm. We had no trigger action response plan. That's for that particular thing. But I was watching and saying, I'm not happy with this, something's going wrong. And that's where all of you guys, when you look at the data, you've got to figure out, is something going wrong? What's my data actually telling me? That's when you start to play with your trigger action. You've got the orange, green, red, whatever they might be, when you take it through. But often a trigger action is, what's the water level? That's probably the first thing when it comes to decant ponds and dams and cleaning. Is my water level too high? What's happening with my whole decant system? Is it not working well? And you can trigger from there.
In terms of the pore pressure transducers example that you gave in yesterday, what was the timeline when you pulled the plug? When you started flattening out, increasing flattening out?
Well, I was watching, I thought, okay, it's going to go down there. And I thought, well, maybe it's still going up. I wasn't sure what was going on. But when it just continued on with a linear trend going up and up, I just thought, hang on, my piezometer is within 5 meters of my water level, where I've got a rock floor downstream. Now tell me how that happens, right? It should never, ever be that close. And so I thought, no, this is wrong. And that's why I pulled it up and said, hang on, I've got to change, something's going wrong there, right? And we fixed the hole, the water pressure's going down. It was rising at about 30 millimeters a day, the piezometric pressure. I just happened to have had a piezometer right there where I should have had it. It was just by chance I had it there. None of the other ones were doing that. None of them, just one. That's the one that can clean.
Tailings are trickier, but can you have like a better workflow, for example, for hydropower dams or embankment dams or fly ash dams? Because we have people on the panel who have worked with that. So do you think there you have a better workflow for like a trigger action response plan? Because for tailings, it's always trickier, I would say, because I think brittle failure is one of the highlighting kind of failures. And as you have rightly mentioned, that it is tricky, but maybe somebody else can mention if there is a better workflow for some other kind of scheme.
Okay. When it comes to the tailings, I belong to the ash tailing dams. So in ash tailing dams, we had seen that brittle failure is not prominent. If we have done the enough instrumentation, it is giving in advance alarming conditions, because the ash is having a very more or less similar properties over the period of time. If ash source is not changing, so the tailing is not changing. So means the coal is coming from one mine or the similar mines, then the properties of the ash tailings are not going to differ much. So if it is not going to differ much, then it comes to the disposal methodology. What kind of disposal methodology. Like in India, we are following the high concentrated slurry disposals, dry disposals, and wet disposals also. So if we consider all those disposals and we can work out what failure modes is coming. So based on that, if we are doing the enough instrumentation, so brittle failure is not probably coming. We have not experienced any brittle failure in the ash tailing dams.
Like any comments on how could we combine like ground sensors and remote monitoring to kind of help us build a fuller or a more holistic picture? Any cases that you can probably that runs through your mind, or would you like to highlight?
Yeah, I guess as was discussed earlier by several presenters, the value of this really comes when you're combining both. Right? So you have fixed instrumentation only gives you point measurements. So you know the pore pressure here, but you don't know anything about what's happening in between. So with these more continuous measurements, whether it be resistivity or other ways of trying to look inside the dam, you can then try to fill in the blanks and essentially use that data to correlate and try to interpolate between your models. But going back to your points about lessons from embankment dams, I think there was something about sort of what type of data we're looking at, and that should really, when you're doing you should almost start with your target. Like, what can I actually put a level on that will tell me something interesting about how close this facility is to failure? And to do that, you need to do your failure mode analysis. You need to know what type of sensor is available, all that. But you also need to do all the numerical analysis, the stability analysis. And those are not straightforward either. They have their own set of uncertainties and limitations in them. So it gets to the point that even if you can measure something, like you said, it's not given that you should measure it. If you can't then link it to some actual parameter, that will tell me something meaningful. So from the embankment dam, there hasn't been much talk about the leakage measurements, but that is sort of the critical almost stethoscope for the embankment dam. Right? Most of the failure modes aren't very brittle. If you measure the leak, you can sort of measure the basic function of the dam. It's supposed to not leak much. All dams have some seepage, but if you can control that, you can very quickly get an alert if something's going on. Now it's a bit more tricky to do for tailings dam, right? Because of the size and the type of materials and all that. But having some type of parameter that can very quickly identify that something is not right is a very valuable thing to put into the card.
I have a question for you, Edgar, because people, when they talk about like data use and interpretation, what they probably we miss is we need to understand the material which we're trying to interpret. So because your talk earlier yesterday, what spoke about like how do we have to rely on laboratory tests or trying to at least understand this material in the very first place before we interpret the data that it's throwing out from its behavior. So any comments on that, like how much is enough or how much effort should be put into understanding the material? Then you know its behavior, and then you sense it, and then you know, oh, it's not really behaving the way it should be, and then you kind of have whatever, an alarm kind of instigated. So any comments on that?
Yeah, I'm gonna go through that same process. Actually, I want to start with, if you rely on an instrument to predict a brittle failure, it's wrong. I mean, it's too late. I mean, the instrument is not the way to control a brittle failure. You need to understand if you are in the presence of a brittle failure by your lab testing, and if you do, you need to design against that. Then everything else is really, really risky. Now, going back to the question, then gonna probably use a simple example. If you are the tailings and you're expecting the tailings to settle or to deform X amount of meters, then you put your prisms. Then your tap is, I'm expecting 3 meters. My tap green is 3 meters or less. Then the dam start moving to 3.5. Then I have my yellow. Then it's going to 4. Then it's my orange. And then 7 is evacuation because something went completely wrong. Then the red should be something went completely wrong. You don't want the guys on site calling you to tell you, hey, we have something here in red. It's because you realize that something is completely wrong and you need to act pretty quick. Then the way how I see how you connect everything is you do your modeling, you predict what your the performance is going to be. You develop the taps based on that. You obviously have a sensitivity, like if I'm expecting 3, but what happens if I go into 4? Then by 4 is not a worst case scenario, but I want my yellow alarm because it's not what I'm expecting. Then you have your expected case, your worst case scenario, and then your emergency scenario. Then that is the way how all my advice is when you are developing tabs. It's no, that should be the, in my opinion, the process.
I think it's a very, very fair point because when we discuss about tailings dams, we're talking about live structures. So the conditions change all the time. By the time you are raising your embankment, you should reassess your design intents, because sometimes you have a set of instruments that's enough for the current situation, but that situation could change when by the time you raise your embankment. So you should update your review your design intents, review your top, and then have a look if you need to increase the number of instruments, or maybe increase or change the way that you are entering your structures on. And we are mentioning about water dams, just because I've been working on this industry for so long as well. To be honest, I think it's quite different industry, because we have one side, we have assets, that's the hydropower plants, the water is the asset, and things is pretty much liability. So it's not common to construct the embankments on liquefied materials on hydropower plants, because it costs to them much more to monitor and to have nightmares to think what could happen when you have liquefied materials on your foundation. So the preferred options, when you think that the triangle, that is elimination of the hazards, substitution or replace the hazard. So we always think in terms of design, and the early stage of design is elimination. What's the way I can eliminate this risk? It's not constructing these embankments on liquefied materials. So I think that's just a point.
Right.
Need to go on with the brittle failure. Where are you on your stress strain curve? Nobody can tell you that, because you don't know what the stress is down there, unless somehow you can measure that stress and understand that stress and know where you are in terms of how close you are to your critical state line. I mean, that's the challenge I think we've got always, is, as you said, understand your material. But we're still going to be faced with that problem, I think, of how far have I gone along that curve before I'm going to suddenly drop off. I mean, obviously, you know, the other ones they went like that. I mean, the one I'm dealing with right now, they have liquefaction in ash. And it was just within 5 minutes, the guys have been working on the dam. They were driving past backwards. They looked behind them literally, and the dam just went and disappeared. Went 500 meters down the road. Nothing went off site, but they were really scared, right? And it was very quick. And it was because they were using very wet material, and they just didn't do the right thing. But anyway, so it can happen quickly. But I mean, that critical state thing and the brittle failures, really, one of our guys, geotech engineer, he always says, do you really understand what's going on down there to be able to predict anything? I don't know how you can get that in situ stress, apart from putting down some kind of probe down there and figuring out the stress there, but you've already disturbed the stuff. And I mean, it's going to be very, very low strength. And I know David Williams always says, when it liquefies, its strength is 0. It's not 2 kPa or 0.03 tau sigma ratio is 0, because it's gone. You know, and at that point, it's gone. So post liquefaction stability, sometimes you think, oh, we're kidding ourselves. I know it's post liquefaction, but has it already gone downstream somewhere before it's actually got to that? I don't know. Comment from how do you monitor for that? I don't know.
A lot of people who work with this critical state in tailings, they say that if there is, if the tailings are liquefiable, it will liquefy. That's their period term that they have. But that's probably, there's no solution to it. We can just say they would liquefy, but they are dams which are like probably upstream constructed, with tailings sitting on weak layers which are brittle. So maybe we cannot predict brittle failures, but can we identify such brittle layers from monitoring, some kind of surveillance, and then, I don't know, be extra cautious? Some comments on that. Like, it cannot be like it's completely doomed. Okay, if we have it, this eventually is going to fail. Any comments or?
Yes, in Indian context, if I say it can be done, because what is happening in India when we are going to construct the ash tailing dams, we are basically trying to use the ash or the tailing itself to construct the raisings, future raisings. So whatever tailings already we are having inside our ash pond or the tailing dams, we can identify the properties in advance, and then we can identify whether it is going to liquefy in the future during operation stage or not. So we have done the similar kind of studies in our ash ponds, and through IITs we have done the similar studies, and it has been observed that if adequate drainage arrangement, internal drainage arrangement below the embankment dams is provided, then it can be prevented. So this way we have earlier in the past, what happened that due to one earthquake, one of our ash pond got breached. So after detailed study, we observed that there was some kind of liquefiable material below the raising. So when we got investigated, then it was suggested that if we could have gone with the ground improvement and the additional measures below the raising construction, it could have been prevented. So I think it can be done with the advanced testing and the identification of the construction materials.
And maybe the next important question is like, as soon as you kind of observe an anomaly in the monitoring or the surveillance data, the owner sits on whom to pull the plug or blow the whistle. Does it sit with the owner? Does it sit with the design engineer, the EOR? Like, whom does it really sit with? So any comments on that? Because that's the part which nobody wants to put their hands on. But
I answer that one.
Yeah.
I would say duty of care.
Okay.
If you identify something, you don't need to wait. You just basically need to say, this is happening. You need to let people know. If the client doesn't want to listen to you, it's a whistleblower. You basically notify them. It's a duty of care. If something happened and you identify it, and you're gonna be taken to court and they're gonna ask a question. Were you aware of this? Yes. Did you report it? No. Why not? Well, I was waiting to see who is gonna make the call. Then duty of care is responsibility of the owner, the EOR, the designer, the people that is making the difference. It's something that is not right. It needs to be notified.
I would like to add in the Indian context that in India, what is happening that a similar problem is coming when we are doing the postmortem in-house by the owner itself. So what we have evolved in our organization that we are involving the third party. Whenever there is some kind of breach or some kind of distress, which is going to affect largely to the larger population. So it's better to engage the third party. If third party is going to say something, then both the designer and the owner and whoever was responsible, they are not able to raise the hand. So that way it helps to identify who was the real accountable person and what went wrong, and that has helped us. So we have evolved such systems.
So also because we looked into like there's going to be so much of data, so we need like platforms to basically integrate all this data and like probably spit out a lot of graphs and data. Like, but we obviously need some human intervention. So how much of human intervention and at what frequency should this be? How can this be designed or decided upon?
I think probably it has to be in the context of the risk level. I think if there's no chance of a loss of life or any major environmental issues, then probably you can get away with a less frequent update. And if it is a high consequence, and you're looking at potentially 100 slides. But I think the key here is that you have to plan for this beforehand, because in a sharp situation, it's already too late if you haven't planned for it. So you need to walk up, who's going to make that decision? How are they going to make that decision? On what grounds are you going to make that decision? Because it's also not an easy thing to pull the plug on an evacuation of potentially hundreds or more, 1,000 if we're talking about large water dams. So you need to be pretty damn sure that it's actually something really serious going on. So yeah, it sort of shows the importance of the TARP, or we don't call it TARP in the water world, but there's that on one side, we have all the planning, we have design, we have the instrumentation system, everything leading up to something going on. And on the other side, you have all the emergency preparedness and evacuation routines and all that. And TARP is really the connection point between all this work. So if you don't get that part right, it is extremely hard to make that decision in the meaningful.
So we're talking instrumentation, but never forget that instrument, right? And I have normalized inspection data, just like Oracle, where they normalize the water coming out. They said, that's normal. I normalized cracking on a TSF, longitudinal cracking. I thought, oh, that's normal. It's just settlement of the upstream raise. That's fine. And the guy said, oh, there's an old water channel underneath there. I said, water channel? Are you kidding me? There's no water channel there. Forget it. And I normalized. I said, that's just normal every year. I came to build on top of that stuff. I did investigation, and our investigation holes went either side of material 10 meters low. The strength was 5 kPa. When we built the dam on top of that, it slid. The guys phoned me up and said, Malcolm, do you know that the dam's moving? I said, are you kidding? Yeah, it's cracking. That's fine. No, they said it's not moving. And it opened up a crack. So I normalized the data that I was seeing every year when I did my inspections. And that was really dangerous. I had to think afterwards, wow. Nobody knew about that, by the way. One person in the company that I was dealing with knew that there was some soft, horrible stuff down there. None of us knew it. And my investigation didn't pick it up. So when you talk about all the stuff with the trigger action, my action should be trigger saying, hang on, this is flat. It's not normal. I need to figure this out and do something about it before I do anything more in the dam to raise it. Because it caused a lot of angst when we had to redesign that whole thing. It didn't fail. It just moved.
I think maybe we can also have some questions from the audience. I was curious if there was any case which you could highlight where you probably had to interpret something and probably pull the plug or say that something was going wrong, or if they're generic questions, they're also kind of welcome. But maybe it's nice to start with a case study. You don't have to name any of the things that we're talking about, but maybe it's nice. But if not, then we are open for questions. We're in the dark, like symbolically, metaphorically. Yes. Yeah. Looks like we really understand and interpret data quite well. Okay, impressive. We didn't need this session. So we basically know how to look at the data, interpret it, and say, this is okay, this is not okay.
Yeah, I think it's just a point to just open my heart, guys. Because I very fascinated with the way that the data management have currently. So have different options, different providers, different vendors. But you should not forget that there is engineering judgment in the data we are receiving. Because as Chris mentioned, I'm not responsible for the data I provide to you. You are in charge to understand the data and to make the call. So, and sometimes when we are dealing with this data, we are interpreting the data, we get some sensibility in how much some VWP varies over time. If this VWP varies because I overloading or constructing quite quicker than usual. So there are a lot of things that you can observe when you are interpreting the data. So it's not because we have a data management, a very powerful tool, so we should neglect the engineering judgment.
So that brings me to the next question, that how much would you rely on automation? For example, the switch from a green to a yellow. Like, because we are probably at a transition where Malcolm believes that it's the brains which probably does the better judgment. But now with so much of data, we probably have to rely on smarter solutions. So where do you think like the switch from a green to a yellow should be automated, relying on like thresholds, which are probably run by these data integration platforms, plugged into by us based on empirical, physical, or experience-based kind of models, but then there should be a human intervention. Any comments on that? Like how much should be the percentage of weightage that we should give to?
The way that I like to assess when we are transitioning from one level to another,
Hmm.
I always looking at some sections next to it, right? Because sometimes you have a malfunction of one instrument, so sometimes the one only instrument with WP is showing that this change in terms of level, threshold levels. So it's important to understand the whole to see if there is like a malfunction of instruments or something happening. Sometimes you have increasing color pressure, but sometimes you have downstream, you have one inclinometer. So we have a couple of things that you have a prism sometimes. So you need to understand the whole thing before you make the call that we are changing the top level.
Something that is important is don't become a slave of your tap. Yeah, that is a just don't sit in there and wait that something turns yellow because it might not, and that doesn't mean that you might not be doing something. Then it is in a similar way. Just don't get taps and it's that all the time they'll be triggered because then people start to ignore them. Then yeah, sometimes with this all now that we rely on getting these big clouds and the data be concentrated in one location. I've seen so many cases where you ask the people on site where the data goes, they don't know. And they finalize a server somewhere that is connected to another server that is down. Then you will never get a tap. Then you basically need to understand the data, look at the data as often as you can, and the tab is just there. It's another tool that you use to identify something really quick when you don't have time to go through the whole data. But don't rely on that. Just like that.
I think Malcolm wanted to.
I just want to emphasize the role of the operator. Never underestimate the role of the operator in doing his daily work, his daily inspection, the boring stuff. You know, when you do a workshop with operators, you say, do you realize how valuable your input is here, right? In taking that reading or checking that there or inspecting that there. When they understand the value that you have for them, it can help in terms of, you know, they've seen something happen, therefore something has to be done about it. In the same way, I get really frustrated that we do not get our drafting people out to the dam sites to check it out themselves. When they do the drafting and you make a mistake and they say, oh, by the way, you can't do that. It's because of this and that. Yeah. So there's lots of things I think we need to kick ourselves in the pants and say, get on with it, get these people out there and do it properly, whatever it might be. You know? But I think I would never, if a trigger went bing and it went from a green to an orange, definitely you're going to have to look at it very carefully and see what's the context. Is it suddenly changed really badly, or is it just like creeping over? But is it a gradual creep that looks like it's treading badly? That's when you start to raise the alarm yourself and say, right, it's triggered, but like me, it just went linearly up, and I thought that's just not normal. Something's happening, and I triggered it. So that would be the same thing. It would be. And they asked me, what's the trigger level? I said, it's that level. I triggered it before I even got to that level because I wasn't happy. You know?
Yeah. Right.
I can always add to that operator part that also think through if there is a yellow alarm or red alarm coming, what is the context that the operator is actually going to see this? So last year we had a small dam failure in Norway. There were no consequences or no major consequences, no loss of life or anything like that. But in that case, there was a water alarm that went off, and no one noticed it, and then the embankment was overlooked. And during the root cause analysis, it was clear that this alarm was triggered multiple times over several hours. But at the same time, they had a 200-year flood event 50 kilometers upstream of this dam. So all the eyes were focusing on that part. And they had something like 200 other alarms that was also going on. Right? So this just drowned in the sea of alarms. So this thinking through, are we relying on manual intervention for something to be safe? Then we really need to have redundancy and make sure that if it gets to a critical level, it really needs to go to the top of the priorities.
I think to kind of sum it up, it looks like it should be a team effort. The people operating on the field and the people sitting in front of the computers analyzing this data, looking at these alarms, they probably should be communicating. And the system should be well understood by all of them to be able to say, this is okay, this is not okay. For example, somebody on the field would have noticed the water levels going up, but they never knew that there was some alarm probably beeping. So I think it has to be an integrated team effort, and you cannot rely on just instrumentation and automated systems that everything would be fixed and you just receive an SMS. It has to be, you still have to think with your brains to accept what the SMS sends you or not. So with that, maybe we can close the session so that we keep time. And thank you to all the panelists. I think it was an interesting discussion. And I don't know, do you want to hand them over with your, yeah.
I'm going to
Okay.
hand you over something.
The
I
rest
think,
all got it.
Vinod and Sasha, I think I've got some presentations for you. The others have already got them, I think, unless.
No, I didn't.
You didn't?
Yeah.
You other guys have? Yeah, all right. So come out the front. Thank you very much.
Good.
You're also good.
We shouldn't be photo bombing.
Who's next? Sasha.
Yes. Thank you so much. Thank you. Thank you. Thank you.
In Melbourne. Oh, sorry. Thank you. Okay, so now we're going to have just a little quick session going back to our exercise. Hopefully you've still got all your exercise sheets because we've now learned how to collect all the data and to interpret it. So I want you to fill out the last two questions, and we're only going to have 15 minutes. I know we've just had lunch, but we've got two choices. We can either go down and grab a quick coffee and come back, or we could start doing presentations. I probably prefer to go down and get a quick coffee and get on with it. But if you don't, anyone doesn't like that idea, all good. We're going to do some exercise first. So grab your sheets. If you haven't got them still, I can hand more out. We want to go over to the back page and look at. We're looking at question 3, trending technology. So wanted to update your design, and then statement 4 is your data acquisition system. What sort of data acquisition system are you going to put in your data? So then go back to your groups or form new groups, whatever you want to do. And don't forget that there's a prize right here, the described piezometer. Hopefully we've got it, and I'll need to be selecting who's the winner from circulating most of the groups to see what it is right now. Everyone happy? Well, that's mine from yesterday. I'm going to give you guys an example.
Sliding scale.
So this is how you're going to say what this stands for. But then you can also the calculation it could be something like visual forms that you go to supervisor or in here, or did you have something like that? That's it. So the operator will effectively put out the times of
Probably know that in the main embankment there is some kind of water flow. Area where there is happening, or in the areas like, for example, the tailings dams, which are kind of maintain the width of the beach, how far the pond is supposed to be to the rest of the main embankment. So, like this is not so sense because maybe as soon as the pond is becoming closer and closer, there would be more areas closer to the dam crest, which would be kind of saturated, not only the right. Also with because then you kind of maybe know that the pond is probably quite far the beach going away. So maybe it's already kind of saturated. Yes, the beach kind of start from here, and the beach is here, it indicates that this for already kind of these are never again become a kind of probably not functioning of these supposedly rock filtering or something like that. Kind of get saturated when they should be disrupting the top layers when they feel such as unsaturated conditions. And the beach or the pond is supposed to maintain quite a distance between the level of the water that they want to maintain. some girls are like, they want the max bracket. This is the max part of the there are a lot of times and even if there's something that the level is higher here and then you have some kind of saturation, that will be separate. This probably is much more important to kind of monitor the resource. Most this end of the main thing is kind of not really getting saturated or remains unsaturated. So this maintenance of the pod or the beach is also very Right.
Which is basically.
Right. But I think Michael was mentioning about there could be transfer rates here. Basically, you should never observe any project, but there shouldn't really be any pressure or something. But the improper functioning of the drains or the clogging of these rock fill dams, it's as you said, it's more like a traffic light connection that tells you that everything is fine. So it's good if it doesn't sense anything. So you can try to unless we both fail, we understand. And I know that here, because of the risk, we know it's not going down. Then, let's say, we also start nothing. The rest of these strong.
That's where you see
It's like post legacy dam or something like that, but there would be other things that there is rainfall if the closure is not good enough and there is too much of seepage which you don't want. There's not enough runoff. There's the issue soil centers could say that ideally when they close it very close to the dam, especially really completely saturated. The closure would be so that at least maybe far away, far to the different depths, not really
speed everywhere. But actually,
It's important. There's waiting here. In my view, and you are is a friction. What the material being strong enough to stop that. It will depend on what is
Okay, I know you're all having fun and chatting, which is really good, but we need to move on. So you can either keep talking and or you can go and grab a coffee and come back and keep talking, or you can talk about something else and go and get a coffee. But I want you to come back by 3:15. Okay, everyone listening? 3:15.
But how much really, for example, statement like the politics, whatever they get in here, they will be some difference in the layers, but they're not different materials altogether. Maybe way, but they're not as different as rock and different like clay, sand. That's the gray area because the resistivity is somewhere a bit different, but it's not a big deal.
The probably not That was also like as a connection here. So here we have a failure of the slope where you feel that there is a right and a preemptive line. And most of the failures dams because they're red, they got listed very heavily. But the really heavy rock, the stability for classic slope failure is kind of less than like Jati's identify the long layers which has saturated. That would be interesting because that's the anywhere it's right, but we should probably look at different sections to be able to show that we can identify this long saturated layer because plastic failure they use them very less. At least the most important because kind of this kind of because they usually come up with this event. But now that's what's something more and more because the
But even if the situation changes, the main issue comes like there is a weak layer here. And then it's fine. What is the entire height of area. It's not that big. Figure out those not sanitary pockets. They actually do not act on, they are dry enough. If that is able to be identified, then that's really nice. It's mostly comes from mind. The crush mind drop, right? It's not really that when they die, everything, they don't process it that much. We were at this stadium, their facility like this. So they were looking just away from the mining process. They don't process it, it's just everything together. So it's very hard. These are particles that the rock might can have fine also. Most course like big chunks of rock, whatever shape, size, anything chunks of rock. But we also thought even in this less one finds to get out from the yeah. Right. They were actually because they were as much as this, they were as small, there was small finer materials, they just process, they bring the dump rock crush and they just dump it and roll it down. Something is wrong.
And then you can use
Yeah, make it less low.
like sliding down.
It's a very local looking food, like whatever is going on. I would not say that's why it's also really like really on the like which product they'll be using from, so they could be different varieties. It's quite a like a big part. It doesn't really sound like anything. Yeah. You need to go to the first starter that. Also have a the starter dam is but that's what it's where. Technically, also they say as much as possible that people can also in the artists you don't have to give it the right like More like even for site, we need people to say that like what we need to do area. Even the sites, even for installing the food, so we can
Okay, so you've all enjoyed your coffee. It's now 2:15. We're back in action again. Did anyone want coffee? Yeah. I did make an announcement that about 10 minutes ago that if anyone wanted coffee, you should rush down and get it and be back by now. But does anyone desperately want a cup of coffee? No? Well, how about we keep going, and if you do really want one later, we can take a break. So we're ready to go. We've done. Okay, so we're now going to go on to look at some case histories. So get Rowan Gleeson up again. We've introduced him before, but Rowan is going to give us a really good case history of a dam in Australia. Thanks, Rowan. It's one that you have to keep a secret, so you can't look at that word on the end of the sentence there.
All right. I'm just going to be running through how we have improved the performance of the instrumentation system at Cadia during construction. So I'll start off by giving you a brief introduction to Cadia itself. Cadia has 3 existing tailings storage facilities and 2 water dams. Let everyone sit down before I start. Yeah, so we've got three existing tailings storage facilities. As you can see there, the NTSF, the STSF, and the PTSF. We're currently tailing into the PTSF as the other 2 are in care and maintenance following the slump in 2018. And we've got 2 declared water dams. We have a capital project which is repairing the NTSF and doing some pretty major buttressing works around both NTSF and STSF. And Spectrum is working with that capital project to look after all the instrumentation. The 2 tailings dams combined cover an area of over 44 square kilometres. So as mentioned previously, they're quite large dams, very long embankments, multiple benches. So there's a lot of ground to cover for the guys doing the inspections. And we've got quite a large instrumentation system with over 620 instruments. And that's not just piezos, there's shape rays, a number of radars, that sort of thing. With all the planned construction coming over the next 5 to 7 years, we've forecast that we're going to see the system grow by over 400%. And that's a bit of a rubbery figure, but we've got a definite 100% growth in the next 12 months just from designs that we've already got So the challenges that we had when the project took over the instrumentation system, take a step back. The project is responsible for the instrumentation for the NTSF and the STSF and the water dam, which is directly adjacent to it. The other two, the PTSF and the other water dam, are still monitored by the site. So the challenges that we had when we took over the system was it was a system that had been installed in a hurry post the slump. So it worked. It did its job, but it was now five years old. A lot of the hardware that had been used was off the shelf, and wasn't necessarily fit for purpose. And because it had been installed very organically, it was very complex with minimal documentation. So that made it difficult to maintain, difficult to diagnose any issues, that sort of thing. And we saw that in a huge number of TARP triggers for loss of instrumentation or loss of comms. So we were experiencing too much of an impact from instrumentation on the construction project itself. And as already mentioned, an instrumentation system that's always triggering the TARP for reasons that people don't think are real is like the boy who cried wolf. People stop believing the system. So the objectives of what we were doing was to develop a system and develop the documentation system behind that to achieve 98% availability, as well as improving the data accuracy and precision and reliable data delivery to the site's user interface, which we use Canary. We started out by developing the design philosophy and design criteria, user specification, and moving from there. So what you can probably can't read, but that's all the documents that we determined needed to be developed. Overarching is the management plan, and then we've got all the standards, the procurement specifications, installation SOPs, ITPs for installation, that sort of thing. And that system has been developed so that we have the full record keeping required for future use. And obviously, being a capital project, we need to hand back a system that's properly documented to operations when the project is done. So the design philosophy that we developed really prioritized standardization and simplicity across the entire system. So we didn't want our technicians to be going out there and opening a cabinet and seeing something different every single time. We want them to know exactly what they're going to see. That makes it far easier to diagnose problems. It makes it cheaper to maintain the system as a whole. But critical spares are, you need less critical spares, you need less models on hand, that sort of thing. And key here is all the instrumentations should inform the TARP. All the instruments, sorry, should inform the TARP. So to start off with, we started looking at the prison network and the total station network and developing a robust survey control. So previously the control had been set out by geotechnical engineers. Nothing against geotechnical engineers, but you're not surveyors. So we had control on the embankment, which we knew was moving. So that's obviously not ideal. So we're still in the process of establishing a robust control network, but the control network really needs to have redundancy in the backsides, cross-bracing triangles in the control network, and the total stations should always be computing using least squares. Previously, they had been set up with just as fixed points, so the total station was never recalculating its own position. So if you did get any movement in the total station, that movement was then translated into the embankment, which obviously gives you false positives. And going with that includes having a proper maintenance calibration and repair regime for not just the total stations, but the pillars themselves. We've got pillars out in the farms, cows can rub up against them, farmers can run into them. So you need to go out there and check them periodically, make sure they're still in place and don't need any maintenance. And the other one was standardization of prisms. So you buy prisms from different vendors, they all have different prism constants, and that just puts you at risk of a transcription error when you're setting the system up. Someone puts in what they think is the standard prism constant, and then it starts to throw all your data out. Criticality. So when we were installing all these instruments and all the existing instruments, we assign a level of criticality to that instrument, and that then determines the effort put into its maintenance, and how we look after it when it does trigger. The criticality of the instrument is really driven by the FMEA. It has to be, it has to come from that. And I need to make the differentiation here between a critical instrument and a safety critical element. So safety critical element, you may not have come across it before, but it comes from process engineering, where if you say this instrument is critical, then that instrument and all its supporting infrastructure that lets it do its job becomes a safety critical element. And if there's no redundancy, then you have to address that and maintain that all that hardware differently. So the safety critical elements can be the instruments, the power, the comms, the cables, and that then flows on and determines how much redundancy they have, how much lifespan you need from them, as I said, the maintenance effort. And then any outages of instruments or safety critical elements are recorded in what we call the bridge register, which also records any TARP events. So redundancy, it's been touched on a few times already. For safety critical elements, we have determined that a redundancy of n+1 in a standby redundancy or cold standby configuration is preferred. So that means, take for example a modem, like a comms modem. If you say that's a safety critical element, you have a second comms modem in the same cabinet. Cold standby means that it's not turned on. So if the one that's operational does go out, you send a technician out there and you turn on the redundant ones. The decision to be cold standby or hot standby is based really on construction and cost. We have some instruments in hot standby where we don't want to wear the cost of stopping construction to, it takes 45 minutes for someone to get out there and flick it over. In other areas where we won't stop construction, we can afford to have it in cold standby, and that just extends the lifespan of that redundant piece of equipment. Integration. So all our instrumentation should be automated with remote access and integrated into a single platform. As mentioned, we have Canary, but we do have some instruments that don't go into Canary. Our radars don't go into Canary at the moment. They're a bit of a tricky one. I understand, Mohit. So currently we've got about 7 different platforms that the dam governance team and the geotechnical engineers have to monitor and then try and cross-correlate to identify trends, which isn't ideal, and it really brings about a lot of decision fatigue for these people who are doing this job. So trying to integrate all the data, as already mentioned today, is very important. And as I mentioned when I was on the panel earlier, the equipment commissioning process needs to define integration and to avoid downstream impacts, like with huge amounts of data flooding your server or saturating your comms. Standardization. I've touched on it already. We have standardized all our cabinets, so they all look the same. That's across different instruments. And it reduces complexity and really simplifies it for personnel training and familiarization. So our technicians, they know exactly what they're going to see when they go to any instrument because they all look the same. The standardisation extends to installation procedures, safety set up around the instrument itself, so they all have a standardised layout, general layout around the instrument. So if they're on the embankment, they have a hand railing, they have a LB park up, that sort of thing. They have bollards to prevent HVs from running into the instrument or our technicians whilst they're working there. And the benefits of standardisation, you can't really understate them. They improve system longevity, they improve problem identification, and they streamline procurement. Saves you money, saves you time. Maintenance plans. We develop maintenance plans for each type of instrument, and every instrument gets regular maintenance. So you may think that some instruments are pretty much set and forget, like a prism. If it's accessible, it should have regular maintenance. That may be at 6 monthly or annual, but it should still be seeing some sort of regular maintenance. So our radars, for example, we do a general inspection on them every week. Then BWP, shape rays, they get a general inspection every 3 months. And this just keeps, it just keeps them in good nick, keeps their power systems working properly. Being in Orange, we get cold winters, short days, solar panels get dirty, the battery systems run out of power, that sort of thing. So it's just, it's helping yourself really, keeping these instruments online and operational. This is a bit of a flow chart of how we manage maintenance tasks, both unplanned and planned maintenance. And I won't go through it too much, but it shows where you have documentation in there as well for record keeping, and different registers where we track all this work that's been done and any unplanned maintenance that's been required. The lifespan of the instruments is pretty critical. We've pointed out that, or we've decided that any non-repairable or non-replaceable instruments should have a minimum OEM lifespan of 20 years. Obviously, that's dependent on how they're installed, how they're maintained, but we don't want to be installing instruments that only have a stated lifespan of 5 years. Shape rays, for example, I think they state 45 years in the manual, which if installed correctly and if maintained. But yeah, the lifespan is determined by the OEM, and then we do everything we can to keep it running for as long as possible. And you need to schedule end of life replacement. And if it's still working, don't be tempted to try and save a few dollars by not replacing it when it hits end of life. Replace it on failure or on end of life, whichever occurs first, because the likelihood is that you'll try and save $1 and then 6 weeks down the track, you'll fail anyway. And then you'll be doing an unplanned replacement. Record keeping. So every single instrumentation, relocation or installation has an ITP that's been developed. We've got personal training and competencies is all recorded and specified in the management plan. Critical inventory is stored. So we actually run a very small sort of warehouse using warehousing principles. And then obviously all the instrumentation installation records, all their calibration certificates, all the zero readings. But you have to have that on hand for the EUR and the DI to be able to set the thresholds. And also the installation records, like the grout records, are very important for problem solving. When you start getting some strange readings from some of these instruments, you can try and work out what's going on with them. Vendor agreements. And we may be lucky where we have pretty deep pockets at Cadia. But vendor agreement, I can't stress how important vendor agreements are, especially for the more complex instruments that we have out there. There's no way my team is going to be able to do medium and long-term maintenance on radars, for example. So you have to have the vendors coming out regularly to do this medium and long-term servicing on these instruments. And it also, lawyers like it because it moves some liability. And something that we're trying to move towards is having the vendors actually host the data from their instruments. So currently all the data goes to a centralized server on site. But with Newmont, they're trying to move away from that and actually have the vendors host that data directly and then just supply the output back to Newmont. Inventory management. Critical to have critical spares on site and to know that you have them. With this, as I mentioned, with standardization, you can have a smaller number of critical spares available because everything uses the same piece of hardware. Everything uses the same batteries, that sort of thing. It's important to, or as I've found, it's important to appoint someone that's responsible for the store and make them accountable for it, because otherwise everything just goes missing. Parts, consumables, tools, they grow legs. So it's important to have a storeman, and he has full accountability and responsibility for that warehouse. And so determining the inventory levels for your safety critical elements is determined by your expected or known failure rate. So if you have the luxury of having a long history of this instrument, or a population of these instruments, and you know their failure rate, then that's great. But otherwise, you work out your expected failure rate of an instrument, and that in conjunction with procurement timeframes, the level of criticality, and any possible schedule impacts that may be incurred, that really determines how much inventory of critical spares you have to have. And obviously, having a good warehouse prevents theft. Personnel. So this is the org chart that we've put forward as part of our management plan for operation. We're obviously in a construction environment, which is a bit different. We've got multiple work fronts, a lot of work going on. So we've got a larger team than this, or twice the size of this actually. But if you have all the documentation in place already and you've got your standardization, you should be able to manage the instrumentation system with a fairly small team. And there are some pretty unique training requirements, and the skill sets for like an instrumentation technician is, as I'm finding, very unique and very hard to find. So all of that comes into the dam monitoring instrumentation management plan for us at Cadia. This document is subordinate to the OMS and supports the OMS. It just essentially provides that greater level of detail. It'll be reviewed annually, but it is a live document which is linked to live registers, and all changes occur in the registers don't actually require too much updating of the document itself. But having this document is really important and has really benefited us in that it's highlighted the importance of instrumentation to all the construction guys, and they finally understand that don't go out and run over a shape array, otherwise it costs the business a lot of money in downtime and in replacing that instrument. So last slide. So the benefits of what we've done, this is the slide that makes it all worthwhile. As it says up there, we've seen a 58% reduction in lost operational time in the last 2 years, and forecasting that looks like we're going to continue to see a good reduction down to less than sort of 40 hours per year of lost operational time. So operational time for us is 6 a.m. to 6 p.m. A 42% reduction in TARP events, and my crowning glory, I suppose, is 39% reduction in the single event duration. So that's the time it takes when we do have a TARP trigger, the time it takes for the instrumentation team to get out there, diagnose the problem, and get the system back online. Yeah, So that's it. Thank you.
Well, I think, thanks, Brian, and I guess maybe people don't understand what those figures mean because the construction operations on site is just absolutely huge. Like you've got the biggest trucks in the world and massive production in millions of tons per annum in construction works going on.
Yeah.
40,000 tons per day. So we've now been lucky to get a last minute presentation from Andrzej Krishnik from Poland. Andrzej is part of, or he's the leader, the manager of the monitoring team at KGHM's dam in Poland, which I understand is one of the bigger tailings dams in Europe, and it's got a pretty amazing instrumentation system by the sound of it. So over to you, Andrzej.
My name is Andrzej Krzyścik. I'm monitoring team manager. I'm working for technical division in big mining company KGHM. We are located in the middle of Europe, in the southwest part of Poland, between three towns: Głogów, Lubin, and Polkowice. Our company, that's our three underground mines, three ore enrichment plants, and two smelters, and one big TSF. Mine product of KGHM is copper, but KGHM is one of the biggest silver producer. We have two facilities, the mine facility, and now we start exploitation with southern extension. Mine facility starts to work in 1977. The southern extension start exploitation in 2021. Mine facility just got the elevation, crest elevation 195 meters. The highest dam height is more than 80 meters. And total area of mine facility is 14 square kilometers. Tailings division managing of the line of pipelines. These are water line pipelines and slurry pipelines, and total length of pipelines is over 250 kilometers. Tailings composition depends on the mine. In Lubin and Rudna mine, the most of rocks, these are sandstones. Polkowice and Sieroszowice, it's dolomite. So the components are sands to silts, and exactly tailings from Lubin and Rudna mine can be used as building material for dams. And we have two different methods for exploitation. Mine object is built with upstream method, and southern extension is downstream method. So our TFS were located in the Kalinówka Brook Valley. We don't have mountains near our TSF. This is 10 times exaggerated. So this is upstream method in the mine facility. On the start, there was built the starter dam with starter dam drainage. After that, it's built from sand from local deposits. The next shelves dams are built from sands tilings. Very important, there are circumferential drainage, which is constructed after we construct the dam crest. We have very complicated bedrocks, so it's mixed by glacier. So we have to use drainage and relief wells. This is a starter dam for mine facility. The mine facility is divided for 26 pigoting section. We spigot tilings on the beach, where its tilings are naturally segregated for sands and more coarse material, and sands are used for building the next shelves. The coarse material is put into the pond, so it seals the bottom. It stops in vertical infiltration to the groundwaters. After filling the spigoting section, we construct the next dam, and it's very important we control compaction. We are using Troxler and laboratory tests and CPTU test for control of compaction. These are fine tilings discharged to the pond. Our decantant system, there are 4 towers with galleries under the dams. And every one construction is divided for 2 stages, increasing dam by 5 meters. Every one stage is 2.5 meters. After this stage, we make additional geotechnical laboratory tests to establish geotechnical parameters. We install additional monitoring devices. After that, stability is calculated, and then we start with another stage. Circumferential drainage is built in almost every 10 meters. These are perforated pipes around the facility, and after that we build the drainage wall. It's almost 10 meters high, and it's very important element of creation of phreatic line. On the southern extension, there is a different method. So we start with starter dam from sands from local deposits. Base dam is constructed from sandy material from tilings, and segregated and compacted fine tilings are located in the middle of the extension. This is a starter dam. Drainage in the southern extension have a different construction. There is a mattress constructed from crushed rock and used as filtrating material slag from smelters, and it's constructed on the impermeable mat. So For exploiting of southern extension, we built the new thickening and segregation station. This is dam core built using coarse granite material. We have to mix this coarse sand for better grind distribution. The fine tilings are just put it into inside. At the bottom of southern extension was covered with clay to stop vertical infiltration. Water intake is flowing intake, and now we are going to monitoring. So we have normal operation inspections. They are provided by exploitation forces. And additional, this is monitoring team controls. These are visual inspection of all objects, especially drainage system, condition of measuring devices, and any observation. And once a month we have building casting. This is a meeting when we prepare data for designer and our experts. Twice a year we have periodic inspection. There is a meeting of designer, experts, TSF representative, and representative of construction law, Polish authorities. And we have special inspection if something happens. These are elements of inspection. So we are using observational method in designing of our TSF. So we are installing a lot of measuring devices. We are make laboratory tests to get ground parameters, and after that the design is modified to avoid any problem. We have two kinds of monitoring. This is research monitoring and warning monitoring. The research monitoring is much more important because we don't want to get warning monitoring. Because we have a long history and we all time we are doing any research, so we have more than 8,000 boreholes in area of Żelazny Most, and a lot of measuring devices. The information is very important for general designer, national expert, international experts, and for building councils. So we have more than 4,000 boreholes, 5,000 CPT tests, open and wide piezometers. In all history, it were installed 5,000. We have 126 inclinometers, 170 relief and drainage wells, and more than 2,000 electroresistivity profiles. In our system, we currently collect information about 30,000 measured points. Measured points, these are places when we have an observation or when we have installed an measuring devices. We are owner of 2 CPT tests, so we almost every day we are doing tests, different kinds of tests. The new boreholes are done and new apparatures are installed. We have together more than 200 cross-section perpendicular to dam, and more than 100 are used for stability calculation. These are geotechnical cross-section. So we are using a different kind of in situ tests, CPTU, CPT-UU, SCPTU, SDMT, FVT, crosshole and downhole. These are geophysical measurements. We bought a special sampler for taking undisturbed samples from uncohesive soils. This is Japanese pusher sampler. We have special apparatus in laboratories, triaxial tests with very high pressures and different kinds of measurements and different kinds of tests to establish parameters of tilings and underlying soils. These are existing working devices. We have more than 1,700 working piezometers, open pipe piezometers. The green one, they are located on the dams for different purposes. One of these is observing or phreatic line. Another is control or working of drainage. Okay, so faster. More than 100 are working in automatic mode. We have almost 400 wire piezometers. And digression is we have better experience with installing wire piezometers with inclinometer. We just saw piezometers reacting for changing of water level in inclinometers, and we had to turn off exploitation more than 30 piezometers. We are using fully grounded method, and we have 123 manually measured inclinometers and 9 automatic. They are quite deep. Now the deepest one is 230 meters. The shallow inclinometers, 28. The shallow have less than 79 meters depth. Automatic inclinometers, most of them, this is SAF-F. These are sharp arrays from measurements, and we have one SAA-V. This is very good way for monitoring underground displacement. So we compared manual inclinometers and automatic, and quality and quantity is very similar. We have 8 tilt meters located on our intake towers. Geodetic points, we manually survey more than 1,000 measuring points. And we have GeoMOS system. This is tachymetric. It's 21 measuring points, and 34, these are GPS stations. We are going to switch off the tachymetric measurement because there is a building area, so we lose visibility of tachymeter and measuring points. These are GPS stations. We have 17 accelerometers and 2 seismometers located on our dams. It's not all network of KGHM seismic devices because mines have own devices on all area of mining. So data are automatically collected in the LITOS system, and after that they are exported to our system. There are more than 700 measuring points of drainage, and very important, these are relief wells. These are wells which have filter installed in cohesive ground. And the role of these wells is to reduce pore pressure in clays. This visual inspection path for all facility, our people have to check all important places. We have linear monitoring system. These are wires around the dams on 4 levels and connected with water level measurement. And we can switch on the alarm for surrounding villages. Very important is collecting geotechnical parameters. So all measurings are taken into calculation of stability. There are used different models for calculation. The last is final elements 3D modeling. We are using LiDAR data for all area once a year. We have to use aeroplane for that, and we use drones for local purposes. Environmental protection, we have groundwater modeling, surface water modeling, atmospheric air modeling, soil monitoring, consumer and feed plants, as well health status of farm animals, human health monitoring, and noise monitoring. We introduced a special system for us, which this is a ORAC database with map and all geological, geotechnical information, construction of our measuring devices and its parameters. It contains terrain models and cross sections, and very important is app for telephones. The mine function, this is collecting of data and automatically sending to the system. And another function is in-field data verification. We are cooperating with Polish companies from different places. They have access to our system. They can to manage with data, use it for calculation and documentation. We cooperate with Polish contractors, with our general designer. This is Hydroprojekt Wrocław. Now we don't have international experts. 3 years ago, they decided to go retired, but it was Professor Jamełkowski, Karl Heck, and Richard Chandler and David Curry. So it's all. Thank you.
Thank you very much. Andre, come over here and our photographer is still here.
Ah, it's done.
Thank you very much for that.
Interesting that shape array matching the failure mode that you have in the filling element analysis.
Yeah. Okay. So next we've got MK. Are you ready? Oh. Okay. He's your colleague. He can introduce himself then.
I have your presentation.
Oh.
Okay, then.
You got it on a USB?
No, he cannot use
Oh.
USB.
Can you use that laptop then?
We can try. Yeah. Hopefully we don't lose the screen. Let's see.
Do you need a USB?
No, he can't.
Okay.
Well, see.
You can send us the PlayStation bill to.
Oh, it's okay. I think it will work. Fingers crossed.
But you lose the Teams or you?
Yeah, lose the Teams. Hey.
What do you Teams back on?
No, I can't because it's his computer.
So good afternoon, ladies and gentlemen. So myself, I am Giri. I am looking after the geotech function at Zawar Group of Mines, one of the group in Hindustan Zinc. And mostly I'm a rock mechanics engineer looking after the mines, and as well as we have tailings dam. So I'm extending my services to the tailing dams also. And I am here with my colleague, Mr. M. Chiara. So in Vedanta TSF, we have almost 9 operations across the globe. And so we will be mostly discussing on Hindustan Zinc. So we have 4 operating mines like Ram, Zawar, RDSK, and we have a smelter, Debari. So this is the surveillance of tailing storage facility that we follow. And so Vedanta tailing goal comments by our senior management. And we have our goal of zero harm to people and environment from tailings, controlling of and monitoring and abuse asset owners, support from COP and COE. COP tailing post support. So that is something we get support from our corporate team. And outcomes, we have an excellent ESG practice and risk estimations and production. So this is about the geotech monitoring that we have at Agucha mine. And you can see this is the dam. And we have a monitoring system consisting of fixed prisms with semi-automated TS, horizontal slope displacements with superficial areas. And we have vibrating wire piezos in place inclinometers. And also we have INSAR. And apart from this, we have physical inspections that we do around all month. So this is the INSAR that we are doing at our TSF facility. So this is common across all of our Vedanta operations in TSF. So we have INSAR working in all mines and giving all sites and giving us almost as per requirement. Some places we have like twice a month and some places once a month. So this is also a real-time monitoring system that we have at our TSF. So we have in place inclinometers and piezometers. So both are online. We'll stick to this. Apart from this, I think many of you people have visited our Hindustan Zinc Limited Zawar facilities, where you saw the dry stacking plant. So this is the Asia's first dry stacking disposal location. So we have a dry stacking plant along with the dry stack. So the video that you are seeing is the dry stacking operation of 4 lifts, 40-meter lift above wet disposal. So this location we have been operating from 1984. So the major key salient features of dry stacking of tailings are the process flow and the stacking designs, the monitoring that we are doing, and the subsidence and piezo monitoring, and the salient benefits of dry stacking. So as I said, this is placed in 40 kilometers away from Udaipur, and this has been operational since 1982 and a total area of around 80 hectare land. So monthly we are treating around 5.2 million ton per annum, of which I have a capacity of 5 million ton for the tailing, dry tailing, and annual tailing generation is currently around 3.94. So the dry stack volume per annum that we are getting is around 2.13 meter cube. So this is the area where we are doing the dry stacking. So the process flow is like from mill tailings, we get around 50% of solid, 50% water, and we thicken it to 65% of solid and then filter it to 84% solids. And then we dry dispose at TSF. And further to that, we do our compaction with proper QA/QC methods. So this is the stack design, and you can see it is divided into two parts. One is the upper TSF and another is the lower TSF. So 474 is the top RL, 434 is where we started doing the dry stacking, and below we have a lower TSF, which is an extension of it, and we have recently lifted it to further 40 meters on top of it. So this is the dry stacking procedure. So what we do is we use these dry tailings through dumpers and through from the conveyor stockpile and transport it to designated areas where we want to stack, and we lay it off. And after that, we lay it off in an area of around 0.3 meters max. Then we compact and then we do the same process over and over again. And we do around 95% of compaction. So these are some of the site pics. On lower part of it, we have also a reservoir for recycling water. So we say that we have zero water discharge, so nothing goes out from the system. We use it back into our mill. So this is the INSAR monitoring, and we have our TARP well laid out. So each month we get a specific recommendations from INSAR mentioning which are the areas we need to look into. So once we get some alarms that these are areas where you need to go and have a look. Some areas we have ground monitoring where we check with our pizzos and the inclinometers, and where we don't have, and there are indications that we have some coherence loss or something, There we go and do a physical check to find if the dam is stable or not, or whether there are any such indications of leakage or anything. So this is the subsidence monitoring, the piezo monitoring layout. So mostly we are, since it is a valley fill, so we are monitoring the downstream part of it, just like. So you can see the piezometers at the end where we are monitoring. And so lower TSF is critical in terms of monitoring. Rest of the area is filled in, it has covered with the mountains. So in terms of tangible benefits, substantial amount of tailings can be, what we do is we also have a paste fill plant. So this is also Asia's first harvested tailing used for backfilling into the mine. And rest of the part is used as for the dry stacking. So you can see the specific freshwater consumption has reduced considerably because we are using the same water back to our mills. And so this is a small demonstration that we made at our site just for people and the management to understand how important monitoring of dams are. So just to give you a heads up, Zawar is world's ancient lead zinc mining deposit. So we date back to 2000 years back. So we try to do things conventionally and much more theoretically and to book style. There was a sound, I don't know why it is not coming. You can have it up. This is a prototype, we used sand. Okay, thank you.
Sparta. Right, so now we've got Leandro Santos talk about Hidden Valley up in Papua New Guinea. Very interesting site.
Hello, guys. Please hold tight. It won't be long, I promise you. I don't know you guys, but my brain is boiling. You know, it was a very good time with you guys. Very dense and variety of options and monitoring, surveillance monitoring. Thank you for all of us that make the effort to make this happen. I'm very happy to share this time with you today, guys. So, how does it work? Oh, the laser. Where's the laser? How does the laser work? Sorry, guys. Not this one.
You just change the,
Oh, sorry.
it's supposed to be this way.
Oh, yeah. Oh, good stuff. Thank you, mate.
No problem, so we just go back to.
I made a mistake, right? Okay, good stuff. So my name is Leandro. I'm from KCB, Australia, and today you're going to be discussing a little bit about case histories of Hidden Valley hierarchy of controls. Pretty much, ideally, we have discussed a lot about surveillance and monitoring. And my intention today, guys, is to give us a different perspective of surveillance and monitoring. That would be my approach when I thought about this presentation for today. So Hidden Valley mine. Oh, I think it's not this. Oh, is that right? Yes, that one. So Hidden Valley mine has a territorial TSF located in the mountainous region characterized by a high rainfall, 3,000 millimeters per year, and a seismic activity area. So Hidden Valley is located in PNG, 200 northwest of Fort Mosby. The latest, yeah, it's here. It's located here. So it's owned and operated by Harmony. It's a South African company, and they process circa 4 million tons per annum of gold and silver. This is the first successful large-scale on land tailings storage constructed in Papua New Guinea. It's a very interesting place.